So I'll be talking about nonlinear perturbation theory and the galaxy bispectrum. So first, I'll be going through nonlinear perturbation theory for matter density evolution, and then we'll be applying this nonlinear correction to the power spectrum. In the second half of the talk, I'll go through galaxy matter bispectrum, and then we'll take a look at some of the current observations of galaxy bispectrum and their results before finally discussing future plans and challenges for observing the galaxy bispectrum. So previously, we had assumed small linear density and metric perturbations, and then we solved the resulting Poisson and fluid equations for the matter evolution. Now, the problem with this approach is that matter is very nonlinear on small scales. So here we have this solid line and dotted dashed line. You can think of them as being effectively the same thing. They are the amplitudes of the matter fluctuations as a function of scale. And so what we see here is for smaller and smaller scales, these density fluctuations get very high. And so what that means is that anywhere we look on small scales, we'll likely have a wrong answer for the density field if we were to use our linear approximation. Now, that was for the density evolution, but the metric perturbations is given by this dashed line is about the same on all scales. And so that's really great because then that means that we can continue to use our linear perturbation theory for the space-time perturbations. But for the matter perturbations, we're going to need to solve the more general nonlinear solutions. So we have the nonlinear Euler and continuity equations that describe the evolution of matter, and these will hold for arbitrarily sized perturbations. And as I mentioned just now, we can continue to use our linear space-time perturbation approximations, and so that gives us our same Poisson equation as before. And since we're on small scales, we can use Newtonian gravity. So putting all of this together and solving the nonlinear Euler-Poisson system gives us a solution of this form. So here we have a solution for the density field that is the linear solution, delta 1, plus a series of increasingly smaller higher order corrections. And the way that we obtained the solution was by iteratively plugging in one of our solutions and then getting out the next term, and then plugging in that term into the equations and then getting out the next term. And so each term, when we go through this, we see that each term is smaller than the last and each term depends on the last. And so what that means is that all of these higher order terms all depend on this first order term. Now this first order term, like I mentioned, is our linear solution. And so all of these higher order terms are the nonlinear corrections to our linear solution. Now here I've written them in terms of x and the conformal time eta, but we'll be thinking of these and calculating these deltas in Fourier space for simplicity of the math. So an easy way to think about calculating these higher order terms is by going through these tree schematics. So let's take a look at just the delta 2 term. This delta 2 term is obtained by taking two linear solutions at different k's, multiplying them by this f2 polynomial that comes out of the math, which is a function of both of the k's. And so it couples these two fields, these two linear fields together, these two at different k's. And so all of these three things are multiplying each other and also multiplied by the appropriate factors of 2 pi and the delta function from just our Fourier transform. And then we integrate over k1 and k2. And doing all of that gives us our second order correction. Now, we can do this for all of our higher order corrections. So for the nth term, we again have it all depend on the linear solutions. So we just take an n number of linear solutions, multiply them, hit them with this nth polynomial, which depends on all the k's, and then integrating out all the k's. Now, these fn polynomials are rather simple to compute, and they just have like this simple recurrence relation that you can just look up. Now, one of the fundamental differences between linear and nonlinear theory is that in linear theory, we assume that all of the perturbations on different scales are independent of each other. But here we see that for the nonlinear terms, that's not the case. These nonlinear terms take these linear solutions at different k's and couples them together via these f polynomials, and depends, in fact, on this coupling. And so these nonlinear terms encapsulate interactions between perturbations at different scales. Now, all of that coupling is encapsulated by these, and all of those interactions is coupled by these polynomials. And so these polynomials are called interaction kernels. And since they couple different k's or different modes together, it's said that these kernels mode couple the perturbations. So here's an example of what the F2 kernel looks like in a matter-dominated universe. And so here we see that it's a function only of dot products between the k's. In fact, it's a polynomial in dot products of the k's. And so we see very explicitly here how it is coupling together these k's. Now we can actually interpret these terms physically to have physical meanings. And so we do that by looking at the density perturbations in real space, or we can do that by looking at the density perturbations in real space after we multiply by the kernels and integrate. And so the physical effect that these kernels have are given by these three terms here. This first term here is the dot product between the linear density perturbations we integrate over D and the gradient of the initial linear field. This encapsulates the motion of the density perturbations due to the gravitational potential from other perturbations. So that's the shift term. The growth term is the constant that gives the strength of nonlinear growth perturbations. And finally, this anisotropy term tells us that the interactions with other modes anisotropically distorts the perturbations. Now we can apply this to our power spectrum. And so by taking the power spectra between these nonlinear terms, we get these nonlinear power spectra. Now, the power spectrum that takes into account the least number of nonlinear corrections is called the next to leading order power spectrum, or the NLO power spectrum. And since the NLO power spectrum is the power spectrum between the nonlinear corrections, and we can rewrite the nonlinear corrections in terms of the linear solutions for the density, then we can just write the NLO power spectrum as the integral over multiple different linear power spectra and some kernels. And when we do that, we get this. So here the solid line is the linear power spectrum, and the dashed line is the linear power spectrum plus the next to leading order corrections. Now, the two big things to notice here are that the next to leading order corrections, so this nonlinear theory, begins to depart from our linear theory at a certain k. But as we go to higher redshifts, they agree down to smaller scales, and they don't really start deviating until a little bit further down. And this is because at higher redshifts, we're effectively looking back in time, and so the density perturbations haven't had time to become very nonlinear yet on these larger scales. And so our linear approximation holds down to smaller scales. And the second thing to note is that the nonlinear power spectrum has these baryon acoustic oscillation wiggles smoothed out a bit, which is not great at low redshifts, but at higher redshifts, we see that we recover them a little bit more because the linear theory holds for a little bit longer. Now, in the linear regime, the power spectrum, or the two-point correlation function, contains all of the statistical information of the field. And that's because the odd-numbered correlation functions are 0, and the even ones can just be rewritten in terms of this two-point correlation function. But nonlinearity moves information from the power spectrum into the higher order statistics. So the next one to look at, the next statistic to look at, is the three-point correlation function, and its Fourier transform is the bispectrum. Oh, sorry, is the bispectrum. And so the bispectrum can actually be a better probe in cosmology than the power spectrum at nonlinear scales. So here's the explicit kind of definition of the bispectrum. And one of the biggest differences between this and the power spectrum is this delta function, which says that these k's need to vectorially add up to 0. If they don't, then the bispectrum becomes 0 because the delta function cancels everything out. So what this looks like if you were to draw these k's out as vectors in k-space and add them up vectorially is we would put them head to toe, and so we would form a closed triangle. So the only combinations of k's that will give you a non-zero bispectrum are k's that vectorially add up to these closed triangles. So the shape of the triangle tells us which combination of k's we're looking at, and the configurations of k's, or the shapes of these triangles, for which the bispectrum is non-zero, is referred to as the bispectrum's shape, and is usually how we differentiate between different models of the bispectrum. So the first model is to use our tree method from earlier to get the matter bispectrum, just like we did for the power spectrum. And so when we do this, this is called the tree level bispectrum. And since we're using the same kind of nonlinear perturbation theories earlier, we can use the same kernels. And just like with the NLO power spectrum, the bispectrum at the tree level can be rewritten in terms of these kernels as well as linear power spectrum. And this holds for large scales, but it starts to break down at smaller scales. And so to extend this tree level down to even smaller scales, we use often two methods. So the first is to use kernels with these extra free parameters, and then just put these parameters to sims. So you're effectively just getting kernels that change the tree level bispectrum to be more accurate down to smaller scales. And then the second is to use nonlinear power spectra instead of linear power spectra. And both of them typically are used. And that's the matter bispectrum. The galaxy bispectrum is basically the same thing, except it has what's called the galaxy bias. So the bias is the ratio between the dark matter power spectrum and the baryonic matter power spectrum, at least in the linear regime. And in the nonlinear regime, we take the linear bias, which here is written as B1, and we add nonlinear bias corrections, just like we did for the density fields. So this first equation here gives us our galaxy bispectrum, and it's almost identical to the matter bispectrum with two main exceptions. The first is we don't have our F2 kernel like before anymore. We have this FG2 kernel. So for the galaxy bispectrum, the kernel changes, and it includes these different bias terms, B1, and then their higher nonlinear corrections. And in addition to changing the kernel, the bias also adds this extra bispectrum noise term. And all of this extra complexity makes things very difficult, but it can also actually be very useful, as we'll see later. And in addition to the tree level bispectrum, we can also use other bispectrum shapes. And the most common ones correspond to specific shapes of the triangles. And so, for example, the squeezed or local shape bispectrum takes as input triangles that look like this. And so this couples the large scales of like very small Ks, for example, and small scales, which correspond to these very large Ks. And is also the equilateral or the constant shape, which uses equilateral triangles, and isosceles bispectrum, which uses isosceles triangles. And this is great or important because different physics phenomena can affect these bispectrum in these different regimes. So multi-field inflation models, for example, change how the density perturbations are coupled together on large and small scales. And so looking at the squeeze bispectrum can probe multi-field inflation as an example. So to look at the actual measured bispectrum, SDSS's BOSS survey in 2015 released their survey with a little under 700,000 galaxies at this redshift range and their calculated galaxy bispectrum. And this is what that looks like. So the bispectrum here is a four-dimensional object, right? It is a function of 3 Ks. And so it can be written and often is written or drawn out with several different plots, each corresponding to different slices in K space. So this top row corresponds to isosceles triangles, in which K1 equals K2, and then just write out the bispectrum as a function of K3. And then the second row corresponds to K2 equaling twice that of K1. And the red and blue points are irrelevant. They just refer to the different data sets that they used. So using this galaxy bispectrum, they were able to break the bias and sigma 8 degeneracy. And they were able to do this because of the extra bias factors that the galaxy bispectrum had. So that extra complexity actually paid off. And they used the bispectrum in addition to the power spectrum for this. They were also able to measure the change in the growth rate D as a function of scale factor A. They were able to measure that from only using clustering data for the first time. And to do all of this, they used the tree level bispectrum, but they used those extra improvements that we saw. So this is the theory curves here are the tree level bispectra theory curves. Now, the results I just mentioned vary cosmological parameters directly and fit the new theoretical bispectrum to the data. So they changed the shape of the shape of the curve for the bispectrum by changing the cosmological parameters. But the bispectrum can also be used as a standard ruler to set the cosmic distance scale. And the idea behind that is that the spectra changes uniformly and scales as a function of distance. So if you change the distance a little bit, it'll scale the whole spectrum, but the shape will stay the same as opposed to varying the cosmological parameters, which will change the shape of the curve. So if we wiggle around the distance until the theory matches the data, then we can set the distance to the galaxies that you use to calculate your galaxy bispectrum from. And we can get the redshift information from spectroscopic analyses of these galaxies. And so we can therefore set the cosmic distance scale, that distance to redshift relation. Now, there are some complications, as I mentioned here. It's a little bit more complicated than that, but that's the general gist. Now, BOSS's 12th data release did just that. They had the largest and highest signal-to-noise galaxy bispectrum. And in 2016, they made the first strong detection of the baryon acoustic oscillation in the bispectrum, found that out at 4.5 sigma. And using this feature, this bow feature, they were able to constrain the distance redshift relation by using this as a standard ruler. And they constrained it down to the percent level, which is a very tight constraint. And they also added one of the tightest constraints, or measured one of the tightest constraints on the linear bias. And in 2017, they were able to use this standard ruler method of the bow to place constraints also on the relative velocity between baryon and dark matter right after decoupling. And this is very important because changes in this velocity can change the number of galaxies that form and will affect the measured distance to luminosity relation. And this is a very important systematic for spectroscopic surveys. So this is yet another way you can use the galaxy bispectrum. So moving forward, the large galaxy surveys of the next generation will be what can most strongly utilize the galaxy bispectrum. And this is simply because they have huge numbers of galaxies. Now, moving forward, we'll be getting billions more galaxies. And large surveys like LSST, Dark Energy Survey DES, Euclid, DESI will all be great for this. DESI as a spectroscopic survey will be very good for the standard ruler approach of constrained cosmology via the galaxy bispectrum. And because the galaxy bispectrum is kind of a fundamentally 3D object, it will be able to get a lot more data than looking at 2D objects like, for instance, the CMB. So galaxy bispectra and matter bispectra in 3D promise to have greater constraint power and are kind of posed to become a potentially even greater probe than the traditionally wonderful probe of the CMB or other 2D data. So future challenges include, to measuring the bispectrum, include that nonlinear bias. So while it did come in handy earlier, the higher order corrections to certain bispectral shapes, like the equilateral triangle, aren't worked out. And so this nonlinear bias corrections definitely poses a big challenge moving forward. Also, we have uncertainties, or any uncertainties in the average number of galaxies will mess with the bispectrum because these average number of galaxies is what gives us our deltas, our overdensities. Galactic extinction, so the scattering and absorption of your signal from galactic dust, particularly on large scales, pose a big problem because certain traces for large scale structure can get screwed up by this galactic extinction. And on these large scales, the large scales for the large scale structure are very important for certain cosmology, like primordial non-Gaussian measurements, for example. And then finally, uncertainties in galaxy distances are introduce more uncertainty on your galaxy bispectrum because the galaxy bispectrum can depend very sensitively on galaxy distances. Now, there is a lot more cosmology you can get out of the bispectrum from what I just mentioned. It's very important for primordial non-Gaussianity. It's forecasted that constrained primordial non-Gaussianities 5 times better when combined with power spectra than just using power spectra alone. It can probe inflation, it can test modified gravity theories, it can break the neutrino mass and sigma 8 degeneracy, it can put constraints on N effective, it can constrain cosmological parameters with the baryon acoustic oscillations in ways that I didn't describe here. It's a very rich and powerful probe. And so as a bit of a summary here, we need nonlinear theory down to smaller scales. And when we're talking about interactions between scales, this nonlinearity inevitably gives rise to bispectrum, and the galaxy matter bispectrum, as you've seen, can lead to a very rich cosmology. And with the massive amounts of data from upcoming galaxy surveys, the galaxy bispectrum is proving and going to be a very powerful probe in all areas of cosmology. Okay, I'm done. I'm technically done. I hit 25 minutes. I just can't stop the video. Oh God, I really can't stop this video.